Hello everyone and welcome to TLE Eliminators. This is Vibhaas, and today we'll be discussing Leetcode Weekly Contest 461. Hi guys, how was the contest? Hmm. Question 4 and question 4. Okay, I see. Interesting. So mostly people are stuck on C and D, I see. Um, I kind of already forgot what C is. What is C? Anyways, okay, let's get into it. Um, Yeah, so before we start, as usual, go check out Eliminator's self-paced courses, which are live now, right? If you want an ordered and structured approach to learning competitive programming, and if you feel like you're stuck at some point, right? You feel like you're not improving or you don't know what to do next, then you should definitely check out these courses because they are made in a very ordered and structured fashion, and they cover all the major topics which you require to reach whatever goal you want. They're even split up into different levels so that you can target exactly what you need at this current stage, right? And some features of the course are more than 40 hours of recorded lectures, 100 practice problems, hints and video solutions for all the problems, as well as doubt support, which is available almost 24/7, as well as a progress tracking leaderboard, right? So if you have doubts on some specific questions, you can ping a mentor. Like there's a system so that you get assigned a mentor. You can ask him your doubts, him or her your doubts, right? So it definitely helps if you do not have like a peer group which is that into CP, or you do not have someone available who can help clear your doubts. So you get doubt support within 10 to 15 minutes at maximum. So do check out TLE's course. Okay. So let's get started with problem A. So as usual, we'll go from the easiest problem to the hardest problem. I know that A and B seems to be not mentioned over here, but yeah, there will be someone who probably wants to even know how to do A and B. So we will start from A, do B, do C, then go to D. Okay. All right. Trionic array 1. You are given an integer array, numbers of length n. An array is trionic if there exist indices such that nums from 0 to p is strictly increasing, nums from p to q is strictly decreasing, and nums from q to n minus 1 is again strictly increasing. Return true if nums is trionic, otherwise return false. Okay. So what do we have to do here? We basically just need to ensure that the arrays of this form strictly increasing, followed by strictly decreasing, followed by strictly increasing. Okay. So here they've given some examples. You can see that this is trionic because 1, 3, 5 is strictly increasing. Then 5, 4, 2 is strictly decreasing. Then 2, 6 is again strictly increasing. So it is following this form of trionic. All right. Now this second example does not, because 2 and 1 strictly decreases and 1 and 3 strictly increases. But there is no increase, decrease, increase kind of pattern. So that's why this is not trionic and the output is false. Okay. So how do we approach this problem? There are many approaches. I'll tell you the one which I found most useful, and it even helped me in the fourth problem, which is a different version of this problem, right? So I'll tell you the approach which felt natural to me. Obviously, there are like hundreds and hundreds of different ways to solve this problem since it can be checked in many different ways. Okay. So now um, you can define this new array. Okay. So for problem A, what we're going to do is we're going to define a new array. Define a new array of let's call it changes. Okay. Let's call it changes. Fine. And a new array or vector which we call changes. And what we do here is from I, which goes from let's say 1 to n, right? What we are going to do is we're going to check whether the previous element to the current element was increasing, decreasing, or stable. Okay. So what we will write is um, basically the value of the change. So let's call that value. Let's set it to 0. And if it was in increasing order, so basically if a of I minus 1 is less than a of I, right? It's strictly increasing. So if you went from I minus 1, which is let's say 3, to I, which is 5. So they're strictly increasing. So we will represent this as a +1. Okay, we'll represent this as a +1 because it has increased. And if it is otherwise, if it's decreasing, so strictly decreasing like this, then we'll represent it as a -1. Okay, as a -1. So for example, if you had a 5 followed by a 3, then these two will give you a -1. All right. So that's what we're going to do. And then one more thing, we will only push the changes when it differs from the previous change. So what do I mean by that? So for example, if you're given an array which is like 1, 2, 4, 3, 2, 1, 5, 7, 8. Okay. Now for this, as you can see here, there is an increase. So this will be a +1. Similarly, here this is an increase. So this will be a +1. Now here there's a decrease. So this will be a -1. Here again there's a decrease, so it's a -1, right? And here again there's a decrease, so it's a -1, and so on and so forth. Now here again there will be a +1, right? There will be a +1. Here again there will be a +1, right? And here again there's going to be a +1, right? So these are the kind of like changes which are happening. It's showing that from the current element to the next element, is there an increase, decrease, or is the value same, right? So if at any point the value was same, let's say this was also 5, then it would show a 0 over here. Okay, it would show a 0 over here. Okay. Now, what do we intend to do? We want to find out if there is some series of ones. After that, there is some series of -1s. Then there should be some series of ones again, right? Then we can say that it is trionic. Does that make sense? So we need to show that there is some series of ones, some series of -1s, some series of ones again, and then this will be trionic, right? So what we are going to do is we only push this value of the change if it differs from the previous value. Okay. So um, if value is not equal to changes dot back, okay, if value is not equal to changes dot back, we push this value into changes. Okay, so changes dot push back this value. Okay, push back this value. Fine. So let me just show how the definition of the changes array is there, and pay close attention to this because in the problem 4 again we use the same problem, the same idea to solve it. Okay. And I think it's a pretty versatile idea. So now what will this condition change about how our array is formed? So instead, what will happen is from 1 to 2, it's a 1, right? So we'll just put a 1 over here. Now from 2 to 4, it's a 1 again, right? It's a 1 again, but that will not be pushed back into our array. That will not be pushed back into array because already the top element is 1 or the backmost element is 1. So it won't be pushed. Okay. Then the next element is -1. So 4 to 3 is a -1. -1 is not equal to 1, so it will be pushed over here. Now this is next one is also -1, it won't be pushed. Next one is also -1, it won't be pushed. Then 1 to 5 is again +1. So this one will be pushed, right? And then this +1 will be ignored, this +1 will be ignored. So this will be our final array. Okay, this will be our final array, which we get from 1 to 4, 3 to 1, 5, 7, 8. Okay, let's take another example as well for this procedure. So please carefully see this procedure once if you haven't understood it yet. Procedure. We're defining a new array of changes. We are going to go through I from 1 to n, and for each value we set value equals 0. If it's less than the previous value, we set -1. If it's greater than the previous value, we set 1. Okay. And then if it does not differ with the last thing which we put in changes, or if changes is empty, in that case we push this value back. Okay. So basically without any repetitions, like here -1, -1, -1 is a repetition, right? We won't get any adjacent repetitions in this array. So we'll just know whether it's like, we'll get to know the broad ideas of whether it's increasing or decreasing and when it changes, right? So that's why I've called this array changes. I'm not sure if it has some formal name or some formal definition, but yeah, that's what I'm calling this array. Okay. And the reason I'm making an array like this is from intuition from past problems. I've seen that it helps simplify problems like this. Okay. Now I'll show you another array and show you how this works. So let's say we have 7, 7, then 3, then 2, then 5, then 10, 10, 3, 2. Okay. So what will be the changes array for this? First, from 7 to 7, there is no change. So this will be 0, right? This will be 0. Then from 7 to 3, there's a negative change. So that's -1. Now from 3 to 2, there is also a negative change, but we won't push this because we already have a -1 here, right? Now from 2 to 5, it's a positive change. So we have a +1. From 5 to 10, again, it's a positive change, but we won't push a +1 now because there is already a +1 on the top. Okay. Now 10 to 10, there is no change again. 10 to 3, there's a decrease. And so we'll put -1. 3 to 2, there's also a decrease, but there's already a -1 here, so we won't put anything. So this will be the final changes array for the given array. Okay, changes array. And as you can see, the changes array shows the broad picture of what exactly is happening in the structure of our array. So for example, we know that our array stays constant for some time. It decreases for some time, then it increases for some time, then it stays constant again, then it decreases. So we have a rough idea of this is how our array is shaped using the changes array. So it's kind of representing the deeper idea of decreasing and increasing order in the array. Okay. So now once we have made the changes array, the only thing we need to check is whether there is a period of increasing followed by a period of decreasing followed by period of increasing, right? So we just need to output this if changes is equal to this array which we want, which is 1 -1 +1, return true, else we can return false. Okay. So this is the final step, else return false. And once you have this kind of an array, it's very simple to just directly answer, right? We directly can tell if it's of this shape or not of this shape. The shape we want is basically something like this, right? Increasing, decreasing, increasing, this kind of shape. And we can easily tell that using this array which I just made. Okay. So the time complexity obviously is big O of n. To make the changes array is big O of n, and to compare over here is big O of 1. So the time complexity will be big O of n. Okay. All right. Let's have a look at the quick look at the code. So here's the code. First, we define n as the size of the vector. I rename the vector to a just to be easier to understand. So a dot size. Then we make our vector of the changes. Then, yeah, this is basically the logic. Has it stayed the same? Has it decreased? Has it increased? That's what we are checking over here. If the changes array is not empty, or if the last value is not equal to the value which we're going to insert, we insert it, right? So we don't want to insert two values which are same one after the other, because we need to know the broad picture. We don't need to know the local pictures, right, of what is going on. And then, yeah, then we simply have our target vector. So our changes vector should look like 1 -1 +1 for this answer to be correct, right? For this array to get a true. So we're just returning is changes equal to target. We just return that, okay? And this will be a Boolean value, true or false, which is what we wanted. Okay. Is this clear, guys? Simple solution, I would say. Yeah, any doubts? Or should we move on to problem B? Yeah, let's go on problem B now. Okay. Okay. You are given an integer weight of length n, representing the weights of n parcels in a straight line. Okay, so we are given integers which represent the weight of n parcels. A shipment is defined as a contiguous subarray of parcels. So a shipment is a subarray of parcels. It is balanced if the last parcel is strictly less than the maximum weight among all parcels in the shipment. Okay, it is balanced if the weight of the last parcel is strictly less than the maximum weight of all parcels in the shipment. Now, we need to select a set of non-overlapping subarrays. That's what it says. Select a set of non-overlapping subarrays which are balanced. Okay, balanced means the last parcel's weight is strictly less than maximum weight of that shipment. So non-overlapping subarrays which are balanced, so that each parcel appears in at most one shipment, right? So that is obvious because it's non-overlapping, and some parcels may remain unshipped. That's also valid. Return the maximum possible number of balanced shipments that can be found. Okay, return the maximum possible number of balanced shipments that can be found. I'm assuming most people would have gotten this as well. So let's take some examples and figure out how to solve this. Okay, so it's a medium greedy problem, I would say, medium greedy problem. Um, Again, time complexity n goes up to 10 power 5, weights go up to 10 power 9. So we're expected to solve this in big O of n. Okay, so let me just write down the weights. The weights are, in an example, let's write down the weights. So the weights are 2, 5, 1, 4, 3. Okay, so here, as you can see, they have given that the answer is 2. And the reason is we can take this as one of our subarrays and this as one of our subarrays. The max over here is 5 and the last element is 1. As you can see, this is greater. Similarly, the max over here is 4. The last element is 3. As you can see, this is greater, right? Okay. So now here, how do we approach this problem? How many subarrays can we make? We need to maximize the number of balance shipments, right? So we need to make the maximum subarrays so that the largest is greater than the smallest. Okay, so our target is to maximize um, maximize number of subarrays where subarrays where max is greater than the last element. Okay, where max is greater than last element. And we need to return the count of how many we can make in such a way. So now, obviously, it's a maximization problem, right? Keep in mind, it's a maximization problem. Usually, how do we solve maximization problems? Usually, greedy or DP should always be considered, right? When you're thinking through how to solve a maximization problem, you should always check the basic techniques like greedy, DP, or binary search, which are used for finding the max, right? And we think about greedy. Okay. So how do we think of being greedily picking the maximum subarray? Well, what we can see is if we have a larger element, if we have a larger element, A of I, followed by a smaller element, okay, followed by a smaller element, A of I plus 1. Okay, so basically what I'm trying to say is A of I is greater than A of I plus 1. Okay, then if we take these two as our subarray, okay, if we take only these two as our subarray, if we take these two as a subarray or a balanced shipment, right? These two as a shipment or subarray, what you want to call it, it will be balanced, right? It will be balanced. It will be balanced. And the best part is since the minimum size the shipment has to be is 2, right? Since the shipment has to be at least 2, otherwise the maximum weight will be the same as last parcel weight, and that will not be possible. So the shipment size must be at minimum 2. So in a sense, it is not affecting the rest of the array much. It's just affecting these two elements. So that's why it's a good idea to take this. Okay. It would be a good idea to take this because it's only removing two elements and the remaining elements are still there to form other shipments if possible. Okay. So from this observation, so basically I can give you an example. Like if we have an array like 3, 4, 5, 2, 15, 20, 8, 4, 3, 6, 2. Okay, if we have an array like this, then every time there is a larger element followed by a smaller element. For example, here, right? Here 5 is the larger element and 2 is the smaller element. So we can take this as a shipment. We assume that, okay, this is one shipment. This is one shipment or subarray, balanced shipment, right? Similarly, any other place where a larger element is followed by a smaller element. So here 20 is larger, so no. And here 8 is smaller. Yeah, so here we have a large element followed by a smaller element. So this can be another shipment. Okay, this can be another shipment. Now we check 4. Oh, and we can have 4 followed by a 3. So that's another shipment, right? And 6 followed by a 2. Okay, that's also another shipment. Okay. Now we get a greedy strategy. Using this example, we can think, okay, maybe we can have a greedy strategy. So we get idea, greedy strategy. Okay, so the idea we're considering right now is a greedy strategy. Can I do this greedy strategy? Right, so I'm going to question that. I'll try to prove it. So basically, first thing to note is that by taking only two elements, by taking only two elements at a time, two elements. I am minimizing the size of the shipment possible, right? I am always minimizing my size of my shipment, minimizing my size of shipment. So what does that mean? That means the remaining elements are maximum, right? Maximum number of remaining elements after removing the shipment. So if I took a shipment of size 3, there'll be less elements remaining, right? If I take a shipment of size 2, there'll be maximum number of remaining elements. So maximum number of remaining elements, and plus one more thing. Okay. And then when you have the maximum number of remaining elements, so you want to maximize the number of shipments, right? So if you have more elements, obviously it will be better to maximize the shipments. The number will not decrease, it will only get better. So if more remaining elements means we could possibly make more shipments. Okay. So more remaining elements. So this is the intuition for why the greedy should be correct. More remaining elements means we should be able to make more chances to make shipments in the remaining elements. Okay, more chances to make further shipments, and because we want to make the maximum number of shipments, this is good for us, right? So this is the rough intuition behind why we are using greedy over here. If you want a formal proof, you can use an exchange argument. So the way we prove greedy questions formally is what is exchange arguments. And so basically imagine that in some valid solution with maximum shipments. Okay, so if you do not follow exchange arguments, don't worry too much. Intuition is what is required for competitive programming. This proof is more formal and mathematical type of thing, which you learn in data structures and algorithms. But yeah, for the people who want a rough proof for why this greedy is true, let's say you have your elements, like you have a bunch of elements. Let's just not give them numbers. Let's just give them variables. And so the way exchange arguments work is we have an optimal solution, and we show that our optimal solution can always be converted to the solution formed by our procedure. Okay, so our procedure is simply we're going to choose two elements next to each other, right? We're going to choose two elements next to each other such that one is larger and one is smaller, and we'll keep repeatedly forming using greedy shipments like this. Okay, so let us use an exchange argument to prove our solution. So assume that the first shipment which was formed was something like this. Okay, assume that the first shipment which was formed was something like this. Then maybe the second shipment which was formed was something like this. And here, as you can see, the shipment sizes are greater than 2. Here the shipment size is 4. Here also the shipment size is 4, right? Here the shipment size is 3. I want to show that an optimal solution can be formed only using shipment sizes of 2 and going left to right. So how do I show via exchange argument? What I can say is here my A2, let's say some element over here must be the largest, right? Some element over here must be largest and it must be greater than A5. Otherwise, this will not be a balanced shipment, right? So let's assume that A3 is the largest. Assume that this is the largest one. It doesn't really matter. So if this is the largest one, then if A4 is smaller than A3, then we can simply take this as a shipment, right? We can simply take this as a shipment. So therefore, we have a shipment of size 2, which is at least as good as the answer, because maybe in that case we could take A5 and A3 as well. Okay, now if assume that A3 is the largest, assume this is the largest, and we'll also assume that A3 equal to A4, right? In that case, A4 is greater than A3, right? A4 will be greater than A5. In that case, our shipment could have been this. Our shipment could have been simply A4 and A5. So using this argument, we can show always that so this is an exchange argument to prove our greedy, and basically if you have any optimal solution with a bunch of subarrays, we can always change the subarrays to form subarrays of exactly size 2. So by always picking size 2 subarrays first of shipments, we can show that the optimal solution will never be anything better than this, right? And so basically what does our algorithm become finally? So this was the proof via exchange argument, that even if we have subarrays of size greater than 2 in a optimal solution, you can always convert that optimal solution into another optimal solution, which can be found using our greedy. Okay, so proof via exchange argument. If you're not familiar with greedy exchange argument proofs, to be honest, my proof skills are also not that great. But if you're not familiar with it, you can Google how to do that. Although it's not necessary for CP. What is necessary for CP is this part. Okay, this part, which is the intuition idea, idea plus intuition part. Okay. Okay. So now what is the algorithm we get after this? All this thinking. So final algorithm, and the final algorithm is um, simply that we need to go from left to right. So for I from uh, let's say 1 till n minus 1, right? So we need to check each element, and we need to check if a of I is less than a of I minus 1. So the previous element is larger than the current element. Here I will increase my count, right? Here I will increase my count and also increase I plus plus. Why will I increase I plus plus? So for example, if I am at 28, right? So if I pick 28 as a shipment, then I can't pick 8 and 4 as a shipment, right? I cannot pick 8 as a 4 as shipment because I've already picked 28. So to ensure that this does not happen, I'm also doing I plus plus while doing count plus plus. So now we can skip trying A4 and we can go to trying A4 3. Okay, so that's why I did this, and that's all. This is the on whole algorithm. There's nothing else to write, and then we can return count. So basically, like 4 lines of code to do this greedy. Okay, so I'll show you the code for this. Yeah. N is the size of the array. I renamed the array to 8 just to simplify. N is the size of the array. Count is starting at 0. So these are the number of shipments which we found. We go from I equals 1 till n. If a of I is less than a of I minus 1, so the current element is lesser than the previous one. So we can make a shipment of size 2. The previous one will be the max element and the current one will be the small element. In that case, I do count plus plus, I plus plus. Once this whole loop is done, I will return the count. Okay, so this is the code for problem B. The time complexity for this is also big O of n. Okay, so time complexity is big O of n. We are only visiting each element exactly once, okay, in the loop. Does that make sense, guys? Problem B is clear. Is it clear? Any doubts? All right. Let's move on to problem C now. Because this was the, I guess, good problem of the contest. Even 4 felt a bit easier. Anyways, problem C. Okay. You are given a string S of length n and an integer array order, where order is the permutation of the numbers in the range 0 n minus 1. Okay, so we are given a permutation in the range 0 n minus 1 and the string S of all length n. Okay, starting from time t equals 0, replace the character at index order with a star at each time step. Okay, we're going to replace the character at index order with a star at each time step. A substring is valid if it contains at least one star. Okay, a substring is valid if it contains at least one star. Also, a string is active if the total number of Hello everyone, is it fine now? Uh, am I audible? Yeah, is it fine? Sorry about that. Actually, I'm in hostel right now. My college has started, so there is shaky Wi-Fi. The Wi-Fi here is pretty terrible. Hello. I'm on data right now, so I guess it won't be that well. Okay, okay. Yeah, actually, when current goes in our hostel, so the Wi-Fi disconnects. I guess I'll need to figure out some solution for that. Mobile data is also not that great, so sorry about that. Um, we'll figure something out from the next stream. Anyways, yeah, moving on. We were on problem. I just read the question. Now we'll go ahead and see how we can solve it. Okay. So basically, what's happening here is um, we have a string, and what we're trying to do here is um, we are given basically at each time at each time we are given which character is being replaced by a star. Okay, which character is being replaced by the star character. Okay, so which okay, at each type we are given which character is being replaced by a star. All right, which character is being replaced by the star. Okay, by a star, and also count how many valid substrings are there. So we have to keep track of how many substrings with a star are present. Okay, and the time when it becomes greater than or equal to k, we need to report the time. Okay, so we need to report the time, report the time, report the time. It becomes greater than or equal to k. All right. So this is what we need to do. Um, right. So how do we keep track of this? How many substrings are greater than equal to k? And so we need to keep. How do we keep track of the number of substrings? Because that's the main thing to do here, right? So ideally, if we could keep track of how many substrings have a star, we would be able to solve this problem pretty simply. So that is what our approach is going to be. So I'm going to give you a rough approach. Okay, so rough approach, and the idea is going to be basically um, for each element. So at each time we're given which element is being converted to a star, right? So at time equals 0, we are given that the first element is being converted to a star. So as you can see, the array becomes the string becomes a star c. Or let's take another example here, right? So here we have the string cat. At time equals 0, the 0th element is being converted. So here you can see it became star 80. Now the second element also gets converted, so it becomes star a star. Now the first position element also gets converted, so it becomes star star star. And the number of substrings which contain a star has become 6. All right. So basically at each step, we just need to know how many substrings contain a star. All right. So for I, let's have a count of star. Okay. Count of subarrays, substrings with star. So let's call that count star equals 0. then what we're going to do for every I from 0 to, or more like every position in order, right? So for every position in order, in the order array, in the order vector, what do I need to do? Count how many, count, or maybe count star plus equal to newly formed, newly formed substrings, substrings with the star at this position, okay? With star, with a new star at the position, whichever position it is, right? With a new star at pos, okay? Then we simply need to check if um, the count of the stars has become greater than equal to k. So count of star substrings has become greater than equal to k. In that case, we can return I, right? Return I means um, so basically we're doing for pos of I in the vector order, right? So this will be the ith position we are checking right now. So if at the ith position, the number of star subarrays substrings becomes greater than equal to k, then we can say that at this time it has become greater than equal to k, so we can return I. Otherwise, we will return -1. So this will be the core like structure of our solution. Obviously, the main part of the solution is not discussed over here, which is how to count this, right? This is the main part of the solution, how to count this, and that is what the whole about, how to solve this problem. Fine. All right. So I hope this much is understandable, right? Guys, is my screen fine? Okay. Actually, I'm using data right now, so it won't be that good. I'm sorry about that. Can't be helped. There's current issues at my hostel. Yeah. Okay. Right. Now, how do we keep a track of how many substrings are formed with a star? All right. So I'll give you an example of a string. So first things first, the letters of the string themselves don't matter, whether it's cat, rat, or ABCD, ABC. It does not matter, right? Only matters where the other star positions are. So we can know that how many newly formed star subarrays or star substrings will be. Okay. So let's say our string is like ABC, EFG, HIJK. Okay. So this is our string. At the time equals 0, at time equals 0, we convert one of the values into a star. So let's say the position we're converting into a star is 4. So position 4 is 0, 1, 2, 3, 4, right? So this position gets converted to a star. This position gets converted to star. Now we need to know how many are the newly formed substrings with a star. Okay, how many are the newly formed substrings with the star? So one substring will be this, right? One substring will be simply this character. The next substring will be these two characters, these three, this, and this. So we can say that at least 1, 2, 3, 4, 5, 6 new substrings are formed. Now we can go like this. So starting at E, we can form 1, 2, 3, 4, 5, 6. Then we can form starting here, and we can end it here, or end it here, or end it here. So there are so many different new substrings which are formed, and we need to keep a track of their counts. Okay, so how do we keep a track of their count? So here we'll use some basic combinatorics idea to keep a track of how many are formed. It will simply be the total number of substrings formed will simply be the number of substrings which include this. Okay, so the number of substrings which include the current position. Okay, which include the current position, or basically the the L value, L value of the substring. So each substring can be represented as L comma R, right? So basically we need that the condition will be L is less than equal to the current position and R is greater than equal to the current position. Okay, so these are the two conditions which we need to find how many substrings are formed using this star. Okay, so using this star, how many substrings are formed. And what will be the count of that? Well, it will simply be this. So this is 1, 2, 3, 4, 5. So these are the 5 different starting points which we can have, right? Um, start here, start here, start here, start here, or start here. So 1, 2, 3, 4, 5. These are the all possible values of L values, right? There are 5 different possible value of L value, you can say. Then what about R values? How many R values are possible? There are 1, 2, 3, 4, 5, 6. So there are 6 different possible R values possible, right? So what are the number of new substrings with a star formed with this? There will be simply 5 times 6. Okay, so number of substrings which have a star in them, or number of new substrings which have a star, will be 5 times 6 for that example, which is 30. Okay, why is it 30? Because we need to include this star, and our L value can be anywhere here, 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 here. This can be the possible L values, and there are 5 different L values. And similarly, our R value can be here, 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 and there are 6 different R values. So using the multiplication rule of combinatorics, it's simply 5 into 6, or number of possible R values times number of possible L values. Okay, so general case will simply be number of possible L values into number of possible R values. Okay, so this is how we count how many are the new substrings which have a star, or how many substrings have this, including this position. Okay, now because this is the first star, there are no other stars to interfere with our count, right? So basically we just need to take I plus 1, and here we simply need to take n minus I, right? We just need to take n minus I. So for the first value, it will always be I plus 1, where I is the position. Let this be the position, or I, right? Position equal to I plus 1 times n minus I, and those are the number of substrings formed at time equals 0, or the first step. Okay, so those are the number of positions formed. I think BS is the best solution. I'm not sure if there's an optimization. I also use BS. To be honest, I used sets, so lower bound. Anyways, I'm getting to that. Now, what if there is a star in the string? All right, what if there is a star in the string? So there's already a earlier star. So we're not time equals 1, we're at time equals 2. So let's say A, B, C, D. Then we have a star over here. Already there was a star. Then E, F, G, H, A, B, sorry, F, G, H, I. Okay, so F, G, H, I, J, K. Right. So at time equals 1, we already have the star. And now we're going to go to time equals 2. Okay, so this is time equals, sorry, at time equals 0, we already have the star. Now we're going to time equals 1, and we're going to convert some position, let's say 7 also, into a star. Okay, next position we're going to convert is 7. So this is position 0, 1, 2, 3, 4, 5, 6, 7. So H gets converted to a star. Okay, H gets converted. I'll mark it. So here I'm marking it, right? Now, how many are the new subarrays? How many new subarrays with the green star, right? With the green star, and we basically need to know that, so we can increase that to our sum. As you can remember, the basic procedure we wrote here is that we're going to go through each of the elements, and we're going to add the newly formed substrings with the star, right? So that's what we're doing here. And how many of those will be? Well, again, we can use the same argument. We need the number of possible L values and the number of possible R values. So the number of possible R values will be these positions, right? So 1, 2, 3, 4. So that is the number of possible R values. So this is 4. Now L values can be a lot of them: 1, 2, 3, 4, 5, 6, 7, 8. Right? There are 8 possible L values. But there is one issue. And the issue is, for example, if we take a subarray, or sorry, substring like this from the start till this point, then it already had a star before, right? It already had a star before. So it was already counted. So if we count it again, we would be double counting. Okay. So if we if we take a substring, if we take a substring which already had a star, which already had an older star basically, then it was already counted. It was already counted. So what would we be doing? We'd be doing what is called double counting, right? We would be counting it twice. So we would be double counting, and our answer would be wrong, right? We would think we have more subarrays than we actually have. So we would be double counting. So how do we prevent that? What we need to do is basically we do not need to go before this previous star, right? We need to our possible L value should stop over here. So this is a possible value, this is a possible L value, and this is it. So there should be only three possible L values. Okay. So basically we should stop just before the previous star, and only we will have then three values, right? So this will be three values for L, and we would have four values for R. Okay. So we would have four values for R. And that is what is the basic idea. We should stop. We should not consider not consider values for L or R for L or R beyond the next star position. Okay, so that's basically it. The stars should be blocked, because otherwise if we count those also, then that would be overcounting the substrings. Okay, that would be overcounting the substrings, and we do not want to overcount the substrings. Okay, yeah, I'm going to include star both in left and right. In this example, there was only a star on the left and there was nothing on the right. But if you have in the next step, let's say we got something like this. So we have A, B, C, D, E, F, G, H, I. Let's say, wait, is the Wi-Fi add again? Just a second. I guess college Wi-Fi is back. Should be better now. Yeah. Okay. Anyways, so we have our so the possible L values will be this, and this. So this will be the possible L values, possible L values, and the possible R values will be this, and so our answer, right? L times R. So that's going to be how much? That's going to be 4 times 3, right? So those are the newly introduced substrings with a star. Okay, so those are the newly formed substrings with a star. Now, basically, for each step, I need to find the previous star and the next star quickly, right? So what remains? What remains? Find previous star and next star quickly. Okay, find previous star and next star quickly. Okay, so that is what remains of this problem. And how can we do this? Well, there's a very simple way. If you know it, you would have gotten this instantly. Store the positions in a set, or even a vector is fine, but set is better since like it will be sorted already. So yeah, set will be definitely better. Store the positions of stars, of previous stars in a set. Then we can use upper bound and lower bound, right? Since the set is the ordered data structure, we can use upper bound and lower bound to find the next star and the previous star, and we can find the number of L and R positions. Okay, I hope my screen is better now, guys. Can someone confirm? Yeah, it's fine. Yeah, so this is what remains. Let me just show you again what I was saying. So I was saying that basically when we have a newly formed star, which is sandwiched between two different stars ahead and before, so we just need to find the previous star on the left, previous next star on the right, and that will define our L values and that will define our R values. So the newly formed strings will only be newly formed between this range, right, which includes this center element. So the answer will be the number of left times number of right, and that will be 4 times 3 in this given example. Okay, in this given example, it will be 4 times 3. Now what remains? We need to find the previous star and the next star quickly. How can we do this? We can store the positions of the previous stars in a set and use upper bound and lower bound, aka binary search, right? Aka binary search. So that's the idea over here. Okay, search. So let's put this all together. So this was a basic binary search combinatorics problem. So put it all together. So again, we're doing the same procedure as before. So there's a count of stars for each position. We're going to increase this. So count is 0 for each position in order. Okay. And what we're going to do here is basically we have to increase the count of stars with the newly formed strings, right? So what we're going to do is next star equals binary search on my set. Okay, to find the next star. So binary search on set. If there is no next star, we will assume that the last ending position n is the next star. Okay, and the previous star will be simply the previous star. If there's no such, then we can take -1 as the previous star. You can see that it will be same on the formulas. Okay, so binary search on set of stars, right? And then left will be how much? Left will be simply I minus previous, and right will be n minus next, right? So position, sorry, not n. It should be next star position minus I. Next star position minus I. Then how many are the new substrings found? We can simply do count plus equal to left times right. Okay, so we can do count plus equal to left times right. And now we have exactly the track of the number of substrings with a star in them. And now we just need to check if that's greater than equal to k, right? So if this count is greater than equal to k, if count greater than equal to k, we can return I, right? Because I is keeping track of what the current time is itself. And then once the whole loop is over, if we have still not found an answer, then they said return -1, so we'll return -1. Okay. So this is the full code of the solution, and the time complexity is big O of n log n because we're using binary search. Okay, and a set as well. So this is the time complexity. That's all, not too hard. We can do this without extra space. That is interesting. Do drop in the comments a summary of how you did that. I could not think of that during the contest at least. Okay. Here's the code. So we have n, which is the size of our string or size of the number of elements to be removed, and count is set to 0. We're using long longs just to keep things simple and avoid overflow while counting. Yeah, and initially we have a set of stars, and I put this to -1 and n. Why is that? Because we can never go if we can never go beyond -1 and we can never go after n, right? So that will satisfy all our equations for next star and previous star, and we can pretend that there's a star at position -1 and a star at position n. That's all this does. Now for each position, or each star which we're adding, I'm going to do lower bound and I'm going to find which is the previous star and find how much difference there is. Similarly, I'm going to do I'm going to do an upper bound and find the next star after this. And then I found my before and after. So this is my left and right. And I increase my count by left and right, left times right. So before times after. So these are the newly formed strings with the star in them. If the count has become greater than equal to k, I can return I because it happened at time I. Otherwise, I continue. I insert this new star in the set and I continue my whole loop. Okay. In the end, even if it's not found, I return -1. So that's the code for this problem. I hope it's understood. Can you explain the counting part again? Okay. So basically, the counting part says that, yeah, so I hope you understood this part. Basically, if you keep track of the newly formed substrings with a star in it, then we can find the answer pretty easily. So how do we keep track of the newly formed substrings? Mm, newly formed substrings, newly formed substrings with a star in them, right? With a star in them. And for this, the only thing which changed in the string at the current time is the current position where the star was added, right? So let's say we had some string where some old stars were already added. So A, B, C, let's say then D, E, or sorry, A, B, C, then E, F, and then there's another star over here, let's say, and H, I, J, K, L, M, and then let's say there's another star over here, and then there's say O, P, Q, R, something like this. Okay, so this was our string, and we choose some position and convert it to a star. Let's say we choose J and we convert J to a star. Okay, so we converted J to a star. Now I want to know how many substrings are there which have stars in them formed by this particular one. Okay, formed by this particular one. Obviously, the ones which were previously there, like this string which is there, this string which is there, which is to count. So how do I do this? Um, so my left position of my subarray of my substring can be any of these three, right? My left position can be any point which includes this star and is towards the left of it. Similarly, my right position can be anywhere over here. So there are four positions for my right position. It can be anything after this, but before the next star, right? So I have two options for my left, three options for my left position, and two options for my four options for my right position, right? So the number of substrings formed is 3 into 4. If you count them out manually, you can see there's 1, then there is 2, there's 3, there's 4, right? So 4 plus, there's 1, there's 2, there's 3, there's 4. So that's another 4. Then starting here again, 1, 2, 3, 4. So total 4 occurs 3 times. So basically it's 3 into 4, right? As we said, 3 into 4. Okay, so that's the number of new substrings formed. This is for red. Why it minus minus? Uh, that's because lower bound gives me the element which is greater than equal to my current position, right? Lower bound gives me the element which is greater than equal to my current position. I want the element which is just less than my current position. I want the star just before me. That's why I do it minus minus. Okay, just think through it. I want the position just before me. That's why I'm doing it minus minus. All right. I want the previous star. What do you mean invalid count? I do not understand what you mean by invalid count. Okay, wait. Okay, so that's Anirudh's solution. Interesting. Okay. So you're doing total number of substrings minus the invalid substrings, and invalid substrings are what? Hmm. Okay, so maybe there's approaches which use lesser space than this, but yeah, I think this is a straightforward approach. Okay, let's move on to the final question now. I'll just go have some water and then we can get into it. The final question is the continuation of the first one itself. Um, Similar ideas will be used. What happened to, is it? Okay, wait, some network issue again. It's kind of hard doing these sessions from hostel. I need to figure out some way to get a better internet connection. Oh, Arin, Arin's approach looks interesting. I don't even think of that, but yeah, that would also work. Anyways, let's go to Trionic Array 2. Trionic Array 2 also can be solved in different ways, like dynamic programming. But I will tell you a simple greedy way to solve it, which does not require too much thinking at all, and is overfin. A simple greedy way to solve this in overfin. Okay. CodeChef Contest 2. Yeah, CodeChef Contest always being explained by someone or the other, right? I'm not sure who's currently explaining CodeChef. Um, Maybe I will volunteer for the next CodeChef. Let's see. Okay. Final problem, problem D. Problem D. Trionic Array 2. Okay. Again, is the same similar type of question. So they're defining what is a trionic subarray. Okay. So trionic subarray is the same thing. It's a subarray in which one portion is strictly increasing, one portion is strictly decreasing, and one portion is strictly increasing again. Okay. Now we need to return the maximum sum trionic subarray. We need to return the trionic subarray with maximum sum. Here observe that nums of I goes up to negative 10 to the 9 till 10 to the 9. So that is a pretty, like, negative numbers will also be possible. So negative sums will also be possible. Also, the length goes up to 10 to the power 5. So big O of n is expected. Big O of n or big O of n log n. Okay. So they have given an array, and here's an example trionic subarray which has maximum sum, right? So now what I'm going to do is I'm going to do this changes array again. So just recall problem one. How did we solve problem one? Here we simply had to check whether it's a trionic array or not, right? And to check a trionic array, we made this changes array, which had a broad view of what were the changes over time for our array. So if it was constant, it would show a zero. If it was a minus one, it means that there's a portion of decreasing. If there's a plus one, it means there's a portion of increasing, and so on, right? So this was what we did last time. And in fact, I'm going to just copy this procedure again for problem A, the procedure which was there, and bring it to this problem as well. Okay. So let me just paste that here. Okay. Right. So we're going to do the same thing. We're going to make an array of changes, and we will have basically then our array will get reduced to something like this, like 1 minus 1 0 1 minus 1 1 minus 1 0 1. And what will that tell us? That will basically tell us that where our array is increasing or decreasing. So if it's a 1, we know that it's increasing. Then we know that it's decreasing for a bit. Then we know that for some time it is staying the same. Then it's increasing again. Then it's decreasing. Then it's increasing, decreasing, staying same, increasing. So we know that the structure will look, rough structure will be something like this, right? And we need to find which part of the structures are trionic, and we need to count what is the maximum sum of such subarrays. So trionic we know means a structure of 1 minus 1 plus 1, right? So here a trionic subarray could be using the elements over here, right? So this kind of structure is the trionic subarray structure, okay? Trionic, right? Now, when we have an array of changes, when we have this array of changes, let's say we have a position where we find a 1 minus 1 plus 1, okay? So then basically the array can have, like, the minus 1 can be any number of elements, the 1 can be any number of elements, this one can also be any number of elements, right? So let's say we have something like um minus 4 minus 2 1 7, then we have a decreasing portion like 4 2 3 minus 5 minus 6, then again we have an increasing portion like minus 2 10. Okay, so basically what we have is something which follows this structure, a trionic subarray. Here at first it's increasing, right? As first it's increasing, then it starts decreasing, then it starts increasing again, right? So this is the trionic subarray structure. How do we find the one with the maximum sum? Okay, how do we find the one with the maximum sum? How do we find the one with maximum sum. Okay. Now, using the changes array of before, we can have some intuitions. So our first intuition will be basically we have like minus ones here, right? I'm sorry, we have like increasing order, so we'll have some increases, then we'll have some decreasing, and then we'll have some increasing again, right? So basically the changes array will look like this only because it won't double count changes. But in a rough view, it will look something like this. Like some are increasing, some are decreasing, and some are increasing again. So when we have such a case like 1 minus 1, 1 in the subarray, then we have to take the elements in the middle, which are decreasing order. Okay, we have to take all of them. Why do we have to take all of them? Because we need a trionic subarray. We need a trionic subarray. So the ones in the middle must be taken. And in this, we can choose. In the ones here, we need one increasing at least. But after that, whether we take two increasing or three increasing on this side, that we can be picky about whether we take one or more. Okay. So basically, what my intuition is basically, whenever we find the pattern, find the pattern 1 minus 1 plus 1 in the changes array, we can form a trionic subarray here. We can form a trionic subarray here, right? Subarray here, and also all the elements of the decreasing portion of the decreasing portion, that is which are minus 1, right? The ones which are minus 1 must be taken in our subarray, right? Because we need an increasing on both ends. We need an increasing portion on both ends. At least one increasing portion should be, at least one element should be there which is increasing on both ends. So one element increasing should be there on both ends. Should be there on both ends. And we can see how much to extend. We can see how much to extend. How much to extend to the left and right. Okay, to the left and right. Fine. So that's basically it. Yes, Prince Raj, you got the idea pretty much spot on. Thank you for that, Sharan. I'm happy to hear that. Okay, so we need to extend the array to the left and right. So we have a portion where it was decreasing. We have to take that, and we have to take at least one which is increasing and one which is increasing on this side. But then we can extend how much ever gives us the maximum sum. So basically, it will be the ones which are till the sum. Actually, we don't need to take non-negative from both increasing. We just, even if there's a negative and there's a larger positive afterwards, right? Then also we need to take it. So for example, well, actually, yeah, we need to take all non-negative because since it's an increasing order, it will start becoming negative after some point. Yep. So let's go back to this example here, which is a decreasing portion. The decreasing portion is 7, 4, 2, 3, minus 5, 6. So all these elements must be added to the sum. Add to the sum. Now the increasing portion will extend until it's required. So the increasing portion we will extend until it's required, right? So 1 and 7 is increasing, so we'll extend here. Now minus 2 and 1 is increasing, but minus 2 just makes our sum smaller. So this is our increasing portion. This is our decreasing portion here. And then we need an increasing portion here as well. So we can extend it to 6, minus 2, but then minus 2 is not the maximum sum. We can extend it even more and we can extend it till 10. Okay, so we get a increasing portion. This is your decreasing portion. And this is your increasing portion again, right? So basically the decreasing portion must be taken whole. whenever you have a 1 minus 1 1 pattern in your changes array, this decreasing portion must be taken whole first. Then to the left and right will extend until it gives us the maximum sum possible. Okay. Rishabh Rajan, in question 1, why is double star not considered a substring? I don't quite understand. I talked about question 3. Even if that is the minus 1, should we take? Anirudh, I didn't quite get. Oh yeah, here it should be minus 3. Yes, this should be minus 3. Thank you for catching that, Anirudh. Your second question, which you said, even if it's the minus 1, should we take? No, we just need to take which is maximum. So what we'll do here is basically we can find the prefix maximum, right? We can find a prefix maximum. So we can take like 2 and minus 2 plus 10, and we can take whichever gives us maximum out of these two. All right, that's all. Okay, so let me summarize what we did here. Let me just write a summary. Summary. Every time the pattern 1 minus 1 plus 1 occurs, the element at position 2. Yes, Anirudh, even if it is minus 1 over here, you have to take it because we need at least one element in the increasing portion. Yes, Anirudh, you are correct. In my example, even if this was a minus 1, we would still have to take it because we need increasing followed by decreasing followed by increasing. So at least one must be taken. Okay, so at least one position which is increasing must be taken, otherwise it would not be a trionic subarray. So you are correct about that. Sorry guys, can't help it. I don't know why current is going repeatedly. I am back on mobile data. Is it audible? Is it audible? This mobile data will not be as good, I guess. Yeah. Am I audible? Is Leetcode down? Okay. I'll just wait. Sorry about that. It will be shaky. I'm using mobile data and the data is not the best here. When current comes back, I'll get Wi-Fi. But yeah. Anyways, where were we? I was giving a summary of the problem. So basically what we need to do is every time the position 1 minus 1 1 occurs, first we can set our sum variable to 0 and we can find the sum of the decreasing positions, decreasing positions, decreasing positions, because that we need to necessarily take. We can't avoid it because it's in the sandwich in the middle, right? So since we need an increasing position on both ends, we must take the whole decreasing positions. Okay, so find the sum of the decreasing positions, then extend the increasing portion on the left, increasing portion on the left and right, on the left and right, left and right, till we get the maximum value of sum. Okay, till we get maximum value of sum. So we can just try all of them and take whichever is the max. Okay, so for the left we can try the suffix maximum, and for the right we need the prefix maximum. Okay, so basically the prefix maximum on the right and the suffix maximum on the left until the maximum value of sum we get. Okay, so that's what basically the whole idea is. Yeah, Omi, that's exactly what I did in um question C. Okay, yeah, you're saying in question C, if I just use upper bound minus minus, yeah, that also works. You're correct. Okay, let's have a look at how we code this up. So just some more comments on this solution. It's just greedy. Using the changes array, we know that, the middle. So the main help we are getting over here is that simply that we need to take all the minus ones. So that simplifies the problem a lot. So then we just need a suffix max in this and a prefix max in this portion. Okay, prefix max in this portion. So it's a greedy idea. I am sure that there will be DP solutions as well. So, but they will be more complicated to think about. I think in a contest, more important than being able to solve optimally is being able to solve optimally in such a way that you can code quickly and you don't make bugs, right? I would say that if you're good at DP, then obviously you can go for a DP solution. But in this problem, it's much easier to think of the greedy solution, right? At least for me, because in this you just need to find the changes array. You need to find whenever 1 minus 1 plus 1 pattern occurs in the changes array. For each of the patterns, you can do you must always take the decreasing portion, and the increasing portion you can take some suffix and prefix which take the maximum. Okay, then you can find the maximum over all possible, maximum over all possible 1 minus 1 plus 1 patterns. Okay, maximum over all the possible 1 minus 1 plus 1 patterns. And that's all. You can print the solution. Okay. How do we code this up? The implementation might not be that easy. And one more note regarding the implementation. While calculating the changes array, the changes array which I defined even in problem A, right? So what was the changes array? Just have a look. This array, where value is 0 if the element it does not change, value is 1 if it increases, and value is -1 if it decreases, and we don't repeat the values, right? So while calculating this, we will also calculate when each block starts and ends. We will also note when each block starts and ends. So we know exactly how much to loop. Okay, we can note when each block starts and ends. Okay, when each block starts and ends. Okay, starts and ends. Basically, we'll have range of each block. Okay, range of each increasing and decreasing portion. Range of each increasing slash decreasing slash constant portion. Okay, constant portion. Okay, and how will we do that? It's simple. Simply like we have this one, so we will have, let's say that this increasing portion starts from position 0 and ends at position 3. Decreasing portion starts at position 3, ends at position 7, and like this portion starts at position 7, ends at position 10. And we can just make some small modifications to this loop. We can make some small modifications. If there's a new value being formed, we can add that to a range. So we can be like, there's a new range which starts at the current value, I minus 1 to I. There's a new range. And if the value is equal, we can simply extend the previous range, right? If value is equal to changes dot back, else if value is equal to changes dot back, then we can simply say that range dot back dot second. So the right value of this range can be increased. Okay, so that's all. We can keep track of where the range starts and ends. Okay, where the current block starts and ends. So that will help us do the loops. That will help us find the sum of the decreasing position. We don't need to do it manually, and it'll help us extend the increasing position on the left and right as well. Okay. Yeah, that is exactly it. I'm not sure how to pronounce this. Looks Russian, but the person who asked this, you can take the max suffix and max prefix, combine them with decreasing in the middle one, and that is correct. Yes. How do you find the max suff and pref? Okay, that's pretty simple. Okay, so we know that this portion is decreasing. So let's say we have a decreasing portion like 10, 9, 8, 7, 6, 5, 4. Now we have an increasing portion on the left and right. So let's say our increasing portion is like -5, -4, -2, 1, 3, 7. Okay. And now we have an increasing portion on the left as well, like 4, 6, 7, 8, 10, something like this. Okay. How do we combine? Well, what we simply need to do is to find the um max prefix, sorry, max suffix of this part. First, we can try only this. We can try only this, or we can try both of these sum, or we can try all three of these sum, or we can try all three of these sum. So basically, we can have best equals negative infinity, current equals 0. Then for I starts at, let's say this value is called L and this value is called R. Okay, so I starts at L, I minus minus, so I goes down one by one. And basically what we're doing here is, so I greater than 0, I minus minus. So we need to make sure that it's still in the increasing array. So while it is still in the increasing array, we can check in many ways. We can be like, if A of I is greater than A of I minus 1, so that will A of I plus 1, so that will ensure that it's an increasing array. If not this, if it's less than equal to, we know that it's no longer there, so we can just break. Okay, so we are one by one moving our pointer to the left, and what we're going to do is we're going to add the current position to the sum. We're going to add the current position to the sum, so we can be like cur plus equal to A of I. Okay, let me just write that a bit neater. So the current sum will be added with A of I, and now we'll compute our best sum. Our best sum will be simply max of um our current sum and our best sum. Okay, so once this loop is done, it will give us the best possible prefix. And so it will check first 7, then we'll check 7 plus 3, which is 10. Then we'll check 7 plus 3 plus 1, which is 11. Then we'll check 7 plus 3 plus 1 plus minus 2, which is 9, and so on. So as you can see, it will find 11 as the best sum, which is this one. Okay, so which is this much. And then similarly, we can do it to the right. We will try 6 first, then 6 plus 7, then 6 plus 7 plus 8, and it will find whichever is the best sum, and it will give that as the right side. So if you have iterator for every position of suffix and prefix, isn't it TLE? No, it is not TLE. This is not TLE. Why is it not TLE? Because this is not TLE. Because consider our array, okay? So I will write our changes array, except I will write multiple elements in our changes array, which basically, I'm just going to write whether our elements are increasing or decreasing, okay? So let's say we have this is the increasing portion, this is the decreasing portion. That's what I represent here. Let's say I have an array like this and something like this, okay? And then -1. So now we know that the -1 block must be taken by for sure. So this -1 block must be taken. Similarly, if we consider this -1 block, this can be taken, right? The changes array for this will look like this. The changes array for this will look something like this, okay? So one possible option is to take something from here. And my second possible option is to take something from here, okay? So now every element in this block, is visited exactly once, visited exactly once, right? Visited exactly once. And what about the elements which are there in between? Like these elements might be visited twice, once as a prefix sum and once as a suffix sum, right? So this block might be visited once like this and once like this, the one which corresponds to this, right? So basically, each element is being visited at most twice. Each element visited at most twice, visited at most twice. As if you observe, we're visiting each element at most twice. So it's actually only big O of n, right? 2 times n is big O of n itself. Because each block is disjoint, right? So this 1 minus 1 block, it does not overlap with the other 1 minus 1 block. There's always the minus 1 will always be away from the other minus 1, because to be a valid block, it must be 1 minus 1 followed by like a 1 minus 1, right? So it's like they can't overlap. So we're not revisiting the elements too many times. Yes, yes. Yeah, this is question D. There's no optimized way to get prefix and suffix. You just manually you can iterate. That's all. Okay, so I'll show you the code. It should become very clear how to implement this. The implementation won't be clear until you see the code. I guess the major part of this is the implementation. It's decently long. You could say that maybe the DP solution might have a smaller implementation. So first we are getting a dot size. We are having a changes array, and additionally we have a array called ranges, which for each change will hold the range. Okay, so basically, for this example, we can see that this is our changes array, right? This is our changes array. In orange, we have our changes array. And in pink, I will give the ranges. So basically the ranges will be for the first block, it will be starting at 0 and ending at 3, right? So this is what corresponds to this. Then this one starts at 4. Sorry. Yeah, so this, no, so this one is starting at 0, ending at 4. Now this one starts at 4 and ends at 7, right? It starts at 4 and ends at 7. Like these represent some numbers which are increasing, right? So this is like 1, 2, 3, 4, let's say. So this will be 1, 1, 1, 1 increasing. Then we'll have a decreasing over here. So let's say this becomes 2, 1, 4, sorry, 2, 1, minus 4, minus 7, right? So that's what this represents. So then these are what the ranges are. So this range from 4 to 7 has decreasing elements. Then the next range will be like from 7 to from 7 to how much? 7, 8, 9, 10, right? So 10. So that will be the range of the next increasing block and so on. So this is just to make sure that we know where it starts and ends. That's just a helper function type of thing. And this can be done simply. So while we are calculating the changes value, while we're pushing back this, we can simply push back the range I minus 1, 1. That means these two elements are decreasing. If the value is the same, we just need to increase the R value by 1. So basically we can just say ranges dot back dot second equals I. So that way we're calculating not only the change element, we're also calculating the range of each of them. Okay. So that's how to implement this. Obviously, you can do it in other ways as well. This is the way I did it. Now I'm finding the size of my changes array. My initial answer is set to negative infinity. Since I want to find the maximum one, I set it to negative infinity. So very large negative number. Now I'm going through the changes array. I'm checking if I find a pattern 1 followed by a minus 1 followed by a plus 1, right? So changes of I minus 1 is 1, changes of I is minus 1, and changes of I plus 1 is 1. Okay. So I'm finding each of these. If it's not there, I just continue and I go to the next step and I continue this. Now, first I will sum the decreasing portion. So starting from ranges of I dot first, ranges of I dot second, I'm just summing that portion up. Now I want to find my best before and I want to find my best after. Run sum is my running sum. So it's my cur value over here. I gave this example. Here the current value I wrote as running sum. Okay, so this is the run sum or running sum. And this is my best before and best after, right? So this is the for the previously increasing portion, and this is for the increasing portion after the decreasing portion. Okay. So I simply just start at ranges dot first minus 2. So the point afterwards, I decrease, I add it to my running sum, and I take max of my running sum. So this way I find the best before portion. Similarly, I find my best after position by taking the prefix maximum. So this is just not, this is nothing but a suffix maximum. This is nothing but a prefix maximum. Finally, I update my answer. Answer is the max of answer and sum plus best before plus best after. Okay. And then finally, once I've done all of this, I can return my final answer. Also, you can note that it is guaranteed that there will be at least one trionic subarray. So there will be at least one position which has 1 minus 1 plus 1. So it won't return garbage. It will always return some valid answer. Okay. That's all to this problem. I did hear that there are DP solutions, but I'm not very sure how to implement that. It gets a bit complicated to do. And also this is big O of n and it's simple to think about. Big O of n. Okay. So now I can take any general doubts if you have for the next 10, 5, 10 minutes. General doubts. You can go ahead and drop in the chat any general doubts if you have any. Yeah, it was just brute force and greedy. That's it. I guess that's why. At least I found the contest easier because usually when it's easier concepts, I solve more easily. My lead code handle is accordance. You can check it out. I've not done lead code for much long. I made an account long ago, but never did anything. I started recently while taking these PCDs. Yeah. Yeah, today's contest was a bit on the easier side. Yeah, I also found C slightly harder than D. Although D I was overthinking a bit and implementation was also a bit longer. So yeah. Um, Contest. Let's just see the rank list. Lead code's pretty slow today, or either is that or my Wi-Fi. Okay, 260. Not too bad. I got some penalty on the second question. Yeah, maybe. How to reach greater than 2K rating? It's practice mostly. It's not anything that special. Okay, if you spend a dedicated 6 months, 1 year to practicing the basic topics, like the same topics which are on TLE Eliminators, those are like the core topics which you need. And once you have your core topics, you can do practice. Once that's done, it's not much. It's like any other skill, right? How do you learn to play a guitar? You need to practice. You need to learn how to use the strings. You need to learn what the strings mean. Once you've done that, you need to practice and play every day. That's pretty much it. Okay. All right then. My code will obviously be added in the description. Usually 20 minutes to 1 hour ish after the stream is over. My code will be added to the stream to the YouTube description, so you can check it out there as well. Yeah. All right then. Um, I don't see much doubts today, so I'll be ending the stream now. Thank you for attending, everyone. Hope you learned something. Again, a reminder to check out TLE's courses, right? Like that is what supports us to have all these PCDs and conduct them regularly after every contest. So yeah, please ask for ad coder. All right, I'll put it in today. Yeah. Okay. All right then. Thank you very much. See you all next time. Bye bye.